one, the title of the diagram, sub-level energy diagram. Sub-level energy, yeah, it shows sub-levels. Sub-levels, you know, are like the 2s and the 2p. Those are two different sub-levels in the n equals 2 shell. So the n equals 2 shell has two sub-levels. N equals 1 shell only has one sub-level. But the name is not really what's used. What's used is, this is called an atomic orbital energy level diagram, or an orbital energy level diagram. We have two. We have the molecular orbital energy level diagrams for molecules and atomic orbital energy level diagrams. And so, let's spell it out. Atomic orbital energy level diagram. The thing about the atomic orbital energy, we want to get the energy levels, so we want some kind of idea of what the energy levels look like for these allowed states for the atom. And so we should draw, so we get a better idea, because when you look at this, it looks like each sub-level, or each sub-level is evenly spaced in terms of energy. If this is the energy, then whatever energy this is, however many joules or how many calories of energy this is, it seems or appears to be the same gap all the way up. And so this chart would end at infinity out in space, right? It doesn't happen like that. What happens is the gaps are big at the beginning, and then they kind of shrink down as you go up. And so what we want to do is, even though this is just Chem 4, we don't want to memorize this. We don't even want to bother memorizing this, because there's no use in memorizing a diagram that's way off, right? And so it's much better just to, if you're going to remember a diagram, to memorize the one that you're going to use through however long, wherever you're going, as far as where it goes. And so we might as well learn the right diagram the first time, even though maybe for some it's confusing because it's not in the book. But what we do, typically it's a line that's used to do it. So we'll have the 1s, and then we got to realize that there's a big jump to the 2s. But is there a big jump to the 2p? No. In fact, we're going to write the 2p over here, because the 2p has a different angular momentum. The 2p has the angular momentum L equals 1. So we'll put the 2p's over here with the 2s's, and the 1s has a different angular momentum, which is L equals 0. Now the angular momentum, you don't have to worry about what that means. This is why we don't write it like they're writing it there, because in quantum mechanics, you gotta, eventually you gotta start worrying about the angular momentum. So we'll set it to the side. And not only that, it helps spread things out, because since there's a little gap here, we don't get things too close to one another. Now this is helpful, because here, okay, we see the subshells or sublevels. Subshells and sublevels are synonymous with one another. But over here we see the shells. You can much more easily see the shells. That is, in the second shell there are two subshells, the S subshell and the P subshell. P subshell has 3 orbitals. The S subshell has 1 orbital. So we have the second shell here. And this more closely aligns with this. It more closely aligns with the periodic table here. And this is the theory underlying the periodic table, after all. The theory underlying the periodic table is, in the first shell, well, we have 1 orbital. 1 orbital can hold 2 electrons, so we can fill it with the first orbital with hydrogen and helium's electrons here. Hydrogen is 1, so helium. So we have 1 block, 1 electron here. So we filled the first shell. Well, helium is the first shell filled, with 2 electrons here. And that makes it stable. So hydrogen can do one of 2 things. Hydrogen can gain an electron, because hydrogen only has 1 electron. So if hydrogen gains an electron, it forms a hydride ion, H-, and now it has a filled shell. Or hydrogen can lose an electron. If it loses an electron, then it just has no valence electrons at all. You can do that. Not everything can do that, though. But there are some things. So once we're at helium, then we filled the first shell, then we go on to the next shell, which would start with, the next shell starts with what element? Lithium. Lithium has one electron, so we use arrows. What do the arrows represent? The arrows represent the fourth quantum number, which is called spin. Although this is kind of blurry. I'm trying to focus this thing. It's called spin. We don't see the spin here. This filling these one electron at a time. Each block represents one electron. So we have lithium here is the first block here. And so lithium can do two things. One, a filled S subshell, it's not special like the filled 1s because there's only one orbital here. You know, what we really need to do is fill the entire shell, not the subshell. So lithium really doesn't want to gain just one electron, because if it gains one electron, sure, the 2s's fill, however, the 2p is still all empty. And so what we do here is lithium, for lithium it's much easier to lose an electron. If lithium loses an electron, then it's got the filled shell here. And filled shells happen to be stable. You know, they have the symmetry to it. You know, it's like a cake. You know, a cake that's uncut is more stable than if you start taking slices out of that cake. You know, start like that kind of thing. So here, or pie. So lithium's like this, and then we can fill this subshell with magnesium, or not magnesium, beryllium. Sorry, with beryllium, like this. But is beryllium unusually stable? No. Beryllium tends to lose how many electrons? 2 electrons. So chemical reactivity-wise, we can lose 2 electrons. We go to boron. What can boron do? Well, boron can either lose 3 electrons or can gain. How many would it need to gain in order to fill this? It'd need to gain a lot, actually. It'd need to gain 1, 2, 5 electrons, right? Well, is boron powerful enough to take 5 electrons from something? Is it a powerful oxidizer? No. So most likely boron's going to lose. It's going to be attacked by an oxidizer. Right? And then after boron, we get carbon. Now carbon is in an unusual situation because carbon's right in the middle. Carbon can either lose 4 or can gain 4. And carbon does both. Carbon loses 4 to form carbon in the +4 oxidation state, like in CO2, carbon dioxide, or carbon gains 4 to form the -4 oxidation state, like in methane. Carbon is electron rich in methane, electron 4. So carbon's right in the middle. It can either gain or lose. If it gains 4, then it fills up this shell. If it loses 4, then it has this shell filled. Then we go from carbon to nitrogen. Nitrogen could potentially lose how many? 5. If nitrogen loses 5, like in nitrate, is it so happy? No, it's not so happy because there's a lot of electrons to lose. Or it can gain how many? 3, as in nitride. Nitride with D. The nitride ion, yeah, there's lots of nitrides out there. They're used in ceramics, and cutting tools, and that kind of stuff, coatings. Lots of nitride coatings. And so nitride, so yeah, or it can do something in between. You know, maybe it's not the most stable. For example, it might not go to +5, it might go to +4, it might go to +1, it might go to 0. Because gaining 3 or losing 5 can be tough. That's a lot of electrons. So it depends on what you react with. And then after nitrogen comes oxygen. Oxygen is going to have oxygen is going to have 2 electrons in 2s, and then if we look at the total number of electrons in 2p, it's going to have 2, four electrons in the 2p. In order to completely fill the 2p's, we need 6 electrons, so it's just 2 electrons short, right? And so, in other words, oxygen should probably gain 2. Has the potential to lose 6. Now, there's another thing that we talk about too. There's something called the duet and the octet. This is a duet, you know, because there's only 2 electrons. Hydrogen, the first period, like to form duets. Duet are 2 electrons. 2 electrons to fill the shell. However, to fill the second shell, you need how many total electrons? 8. 8 we call an octet. So if we have an octet of electrons, it's totally filled. If it's totally filled, it's happy, it's stable. And so an octet, which means 2 in the S subshell and 6 in the P subshell will give it a total of 8. And so oxygen needs 2 more, and then fluorine needs just 1 more. And the neon doesn't need anything. Neon is happy as is, and neon has an octet. It's happy, it's not going to react. It's not going to want to lose, it's not going to want to gain. Just as if. And so this is kind of the theory underlying this is the quantum mechanics. And we see that the periodic table was originally based just on observation with no knowledge of orbitals or anything else. It was just based on how things react or behave. And then we see that we can understand the periodic table based on these orbitals. So let's keep drawing them. In the next shell, what do we have? We have the 3s, and then we have the 3p, and then we have the 3d. Do we have the 3d in the next shell? No. And so in the third shell, we just need an octet. However, in the fourth shell, we don't need an octet. We need something else if we wanted to completely fill it, but we'll see that there are some differences here that we don't worry. In the fourth shell, we're going to have what comes first? 4s. Actually, you know, we could see this from the periodic table. Because if we know the periodic table, then the fourth shell's right here. It's the 4s, the 3d, and then the 4p. How many total electrons is that in the fourth shell? Let's count them. 4s, 3d. 3d has how many orbitals? 5. And then the 4p, I'll have to erase this to put in the 4p here. So count them. How many electrons total to fill the fourth shell? Because this would be it for the fourth shell, because the 4... What about the 4d? Well, the 4d go on the fifth shell. And so in this shell, how many total electrons? 18 electrons. So we have the duet, we have the octet, and then we don't have a fancy word for 18, so we just call it the 18 electron rule. There's an 18 electron. But it's okay, we don't, the 18 electrons is not discussed now. 18 electrons is discussed later. But the D is very interesting, the way it behaves, because the D is kind of out of place, you know, 4s here. And so D behaves a little differently than the 4s do. You know, because this is a 3, these are 4s. Now, one of the differences between a 3 and a 4 is, the size, of it. So n equals 1, it's smaller, right? And then n equals 2 is higher energy, so higher energy is bigger, right? N equals 3 is bigger, n equals 4 is bigger. It kind of goes by the square. If you try to visualize how big, then you just take n squared. So n equals 1 is like this. N equals 2 would be 4 times bigger. N equals 3 would be 9 times bigger. N equals 4 would be like 16 times bigger. It behaves that way. And so, these are kind of big compared to this. This is a lot smaller in terms of spatial size. And so these are little things we keep in mind that go through this. So we'll talk more about this in the next chapter. But for right now, we're just going to leave this. And so this gives us a better understanding of what's happening, at a more fundamental level. And so if I got electrons in the s, let's say I got electrons in the s, I have some 1s orbital here, and I have 2 electrons in there. So electron, 1s orbital. The next allowed energy would be the 2s, which is just big, and then the 2p's like this. So we can kind of visualize the electrons are here in the 1s. When we visualize that, we can't pinpoint the electrons, so we have some kind of cloud, like this. 90% probability boundaries. So we can come up with a picture. We don't picture orbits, we picture these clouds, and we aren't looking at the clouds in detail, so we aren't really going to worry about it. Now, is this table easy to draw? Well, don't copy this table, please. Don't use this table in the book, and don't call it a sublevel energy diagram. Call it an energy level diagram or an orbital energy level diagram. Okay, so that's a bit cumbersome. So what we're going to do is we're going to write this in the shorthand notation. But when we write it in a shorthand notation, we also lose some information. And so obviously a diagram like this is going to give you the most information. But a diagram like this takes up space. And so there's something called an electron configuration. An electron configuration just is a compact way of writing this in a shorthand manner. And so, for example, hydrogen has electron configuration 1s1, which means in the 1s orbital we have 1 electron. Helium has electron configuration 1s2. Okay. Sometimes we call this, with square brackets, He, core. Talk about core. We'll put that later. And then lithium. Lithium has 1s2. It's completely filled, and then it has an electron in the 2s1. So sometimes what we'll do is we'll abbreviate the 1s2. We'll say that has the helium core, because that's all what we call, and then the 2s1. The core are usually untouched in chemical reactions. We don't want to screw up the core. We're just going to mess with the outer electrons here. The outer electrons are called valence electrons. And so if any chemistry happens, it's going to happen with the valence electrons, because we don't want to mess up the core electrons. Now the valence electrons, these are defined as the highest end level. Highest end level. Well, the highest end level are going to be what we call the outermost electron, because if n equals 4, it's 16 times, right? Versus n equals 3 or n equals 2 or something like that. And so the highest end level electrons. And so in terms of electron, this is 1 valence electron and 2 core electrons here. We've got 1 valence electron, I could lose it to form a lithium ion. And then after lithium comes beryllium. Beryllium is going to be 1s2, 2s2. So this one's going to have 2 valence electrons and 2s. So this is going to be helium, the core, plus 2s2. Core electrons, again, we don't. Beryllium to boron, this is kind of repeated what we're talking about. This is 1s2, 2s2, and now the 2p's we're just going to group into 1. The 2p, what's the maximum capacity of the 2p subshell? Max capacity is 6 because we got 3 orbitals. But here, in this case, we only have 1 electron. And so this is going to be 2s2, 2p1. And so this is going to equal helium core with a 2s2, 2p1 valence. And so boron has what we call 3 valence electrons here. 3 valence electrons. This makes sense because boron can lose those 3 valence electrons. If an oxidizer comes along, it's going to see these ones. The core are there, and then like 4 times farther out would be the valence electrons, kind of one way of visualizing this. So if you're an oxidizer, you're going to attack these electrons. Probably attack the P first, and then nab the S's, because they aren't that different in terms of energy. You're an oxidizer. And then we got carbon at 1s2, 2s2, 2p2. So carbon has 4 valence electrons. So this is helium, 2s2, 2 of the valence electrons in 2s, 2 electrons, valence electrons in 2p, so a total of 4 valence electrons. After carbon, we have nitrogen. Nitrogen's 1s2, 2s2, 2p3, which means that we got the helium for 2s2, 2p3. Nitrogen has 5 valence electrons. So we need, in this shell, we need how many to fill? We need 8 valence electrons to fill, so it's 3 short. Filling, or we could lose 5 and go down to the helium core. Oxygen is 1s2, 2s2, 2p4, which means it's going to be helium, 2s2, 2p4, 6 valence electrons total. 2 plus 4, 6 valence electrons. Nitrogen, 1s2, 2s2, 2p5, which would be the helium core, 2s2, 2p5. Oh, did I screw that up? 7. Yeah, I screwed this up. I'm doing I shouldn't do nitrogen. I gotta go the other way. Oxygen, nitrogen. It goes the other way. Oxygen to fluorine. Sorry. Fluorine has 7 valence electrons. And then finally, when we hit neon, this is what we got. We got 1s2, 2s2, 2p6. And so, yeah, the helium is filled, but also its valence is filled. And so if you look at the valence shell, it's a filled valence shell. Well, that's stable. And so we call this the neon core. And essentially everything's like core electrons. So this is done. So we can see, based on the periodic table, we can write electron configurations quite easily. Yes?
So if you were to go on to sodium after that,
Yeah.
so would you do all that, but then to dumb it down, would you use the neon here?
Yeah, we would use neon so we don't have to write all that out. You know, for sodium, there are 2 ways of writing it. For sodium, we could write everything out. 1s2, 2s2, 2p6, 3s1. Or, you know, for sodium, we would just write, it has the neon core and the 3s1 valence, which is 1 valence electron. So, if we look at all these, the alkali metals, they all have 1 valence electron. You know, 1s1. These all have 1 valence electron. All the other electrons are in a core. So after neon core, we have the argon, the krypton, etc. And the alkaline earths all have how many valence? 2 valence electrons. The valence electrons are where the chemistry happens. The core electrons are not touched. So we use the periodic table to tell us about the shells, you know, and not all of them, because these are just the ones in which there are electrons. In other words, these are what we call the ground state. The ground state is filling up the lowest energy orbitals first, but if you excite the electrons, then they can get promoted to higher energy orbitals. Which aren't shown in the periodic table. So here, if we go to the okay, we call these periods. So the first shell is the first period. The second shell is the second period. The third shell is the third period. Fourth shell we did. That's what we wrote our diagram. So we have the 4s, 3d, 4p. Now the fifth shell consists of the 5s, the 4d, and the 5p. So the fifth shell follows the 18 electron. It's going to take 18 electrons to completely fill this shell. Now the sixth shell is tricky. The sixth shell is tricky because it goes 6s. But they didn't want to make this table too long. And so what they did was they go 6s, and then they tell you to drop down here. And so the sixth shell goes 6s, drop down here to 4f. Otherwise, you'd have to insert the 4f in here. This table would get very, very long. Because the 4f has 7 orbitals for a total of 14 electrons. Therefore, we need 14 blocks. Each block represents one more electron from an element. And so here we go 6s, 4f, 5d, 6p. That's the sixth shell. This periodic table, it doesn't show it so easily, but in all standard periodic tables, you can see it pretty easily here. How you can tell, it's very easy to tell. You know, once you get to the sixth shell, once you get to the sixth shell, 1, 2, 3, 4, 5, sixth shell, we go 6s. Okay, it's a little bit trickier here because it turns out the 5d and the 4f, the gap in energy is so small. They're almost the same energy, right? And so it's very tricky because we follow the numbers. 55th electron goes here, 56 electrons. So 56 electrons will fill up this up to here. Now what comes after 56? The 57th electron goes here. So the 57th electron goes into the 5d. But where does the 58th electron go? Into the 4f. Remember, they aren't that different in terms of energy. So it turns out that this is lower in energy. You can't really predict this, right? Well, we just look at what's observed, and this is what's observed. You could predict it if the quantum mechanical calculations were pretty accurate. But anyway, the 57th electron goes here, but the 58th goes here. From the 58th through the 71st. So the 58th goes into cerium, Ce, and the 71st goes into lutetium, Lu. These are called the, you know what these elements are called? These are called the lanthanides, and these are called the actinides. And so this whole row is the lanthanides and the actinides, and these are called the rare earth elements. These aren't that common. Rare earth elements. The rare earth elements are really important for computers and electronics, and they're mined in various parts of the world. Rare earth elements. Like samarium, big one. Neodymium. Neodymium magnets, you've heard of those? Very powerful magnets. So a lot of these are very useful for technological applications. Of course, uranium, plutonium, those are radioactive. Thorium's radioactive, actinides. A lot of these are man-made. Plutonium's man-made, neptunium's man-made, americium is man-made, californium is man-made. A lot of these man-made elements. But anyway, so basically you can kind of tell what the shells are just by looking at the periodic table up to a certain point. But beyond that point, then we need all the little rules that we had to build the table higher and higher. In other words, the chart higher and higher. All right, so what we can do is we can do electron configuration. So for example, let's do the electron configuration for arsenic. Well, we could fill up an energy level diagram. If we fill up an energy level diagram, we have a map here to fill it up. Or we can do it the compact way. And doing it the compact way is probably what we're going to be doing. And so what we do is we use the periodic table to generate the electron configurations. You have two choices. You can do it without using the noble gas cores, or we just do 1s2, 2s2, 2p6, 3s2, 3p6. Then we go to 4s2, 3p10, 4p1, 2, 3. so we can write it all out. 1s2, 2s2, using the periodic table, 2p6, 3s2, 3p6, 4s2, 3p10, 4p3. Or we could use the core. If we use the core, up to 3p6 would fill argon, right? And so another way of representing this is argon, 4s2, 3d10, 4p3. Now, I told you like this subshell, like an S subshell, having it filled versus half filled doesn't make a big difference, because a half filled subshell of an S, symmetry-wise, is still spherical. But a D makes a bigger difference here. And so, or we do it like this. This is how it fills. So this is the filling order here. The filling order, interestingly enough, is not the same as the removing order. If I'm taking electrons away from this, let's say I'm an oxidizer, even though the electrons fill this way, the electrons are not going to be removed this way. The electrons are not going to be removed this way because if you're an oxidizer, you're going to take the electrons that are closest to you, whether they're the lowest energy or not. And so, yes, I know I filled the 3D before the 4P, so that means the 4P are higher in energy. And so if I'm an oxidizer, well, you're going to take the electrons closest to you. Which electrons would be closest to you? The highest energy, the furthest out, which would be the 4p. And so if you're an oxidizer, you pluck off these 3 4p's first. So arsenic, one charge on arsenic, AS, AR is argon. One charge on arsenic is +3. So if you're an oxidizer, you come in, you take off the +3, so we get arsenic 3. Or in your nomenclature, arsenous, right? But, you know, if you're still hungry for electrons, and you're a powerful oxidizer, you can continue removing more electrons, right? Well, this is rich. There's a lot of electrons there. But one thing that prevents these electrons from being taken is it's filled. It's a 3D subshell. 3D subshells that are filled are pretty stable. The other disadvantage of this is this. As far as distance goes, these are higher in energy, so they're maybe sweeter for the oxidizer to take. However, they're farther away. You know, if you're an oxidizer and you want to take these are 9 times the distance from the nucleus. These are 16 times the distance from the nucleus. And so when it comes down to 4s or 3D, 4s are a little bit more difficult to pluck away because they're lower in energy. A little bit more difficult to plug away. How much more? Not that much more, because these are all in the same shell, right? Than the 3D. But the 4s are much farther away from the nucleus. So for an oxidizer, it's easier to plug away. And so we have an alternative way we do this. The alternative is like this. It's argon, 3D10, 4s2, 4p3. The reason we do it this way is because of this. These are going to be the valence electrons here. The valence electrons are the 4s2, 4p3, and then the 3d are going to be inner shell electrons. And so inner shell electrons are core, inner shell. Now, 3d are much closer to the nucleus. And so really, you might think, okay, this can lose up to 17 electrons. It's not. Or not 17, 10 plus 5 is 15 electrons. It's not. We'll lose max of about 5. And maybe you could lose more, but it'd be pretty difficult. And so we have this type of situation. And so arsenic has how many valence electrons? 5 valence electrons. And so all these have 5 valence. Nitrogen has 5 valence electrons. Phosphorus has 5. Arsenic has 5. Antimony has 5. You know, even bismuth has 5. And bismuth is going to have a filled D and a filled F. But those aren't considered valence. Now we could have a partially filled. And And so let's go to something like iron. What is the electron configuration for iron? So let's find iron here. Iron's element number 26 here. And so what we can do is we can do the shortcut. We'll start from argon. Argon's 18. So we'll start with 18 electrons at argon. So here this takes us to 18 electrons out of the 26. And so the 19th electron is going to go where? 4s, and the 20th electron is going to go in 4s. So we're going to have 4s2, and then we'll just go across this. This is going to be 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d6. So this is going to be 4s2, 3d6. If you're an oxidizer, which electrons are going to be more appealing to take? The 4s2. Even though the 4s2 are lower in energy, more stable, and the 3D are less stable, higher in energy, the 3D, the oxidizer has to really dig deep into the atom to get those, versus the 4s are on the outside, outermost. And so those are the outermost. And so really, when we're thinking about argon, I would say argon has 2 valence electrons. This is 3d6. 4s2. And so if an oxidizer comes along, it's going to pluck these 2 valence electrons here, and that's going to result in iron plus 2. Now, if it's a powerful enough oxidizer, it might strip an inner electron. It could strip an inner electron here because the 3D is not a fill. And so, not being a fill, like 3d10. 3d5 is good, and 3d10 is good. Like a half-filled has a symmetry. We're talking about like a cake, like this. If you take a slice of cake out of this, then it loses its symmetry. You know, it's not stable. So if you look at all the 3D orbitals and combine them together, if you take all the 3D orbitals and combine them together, it forms a sphere, kind of spherical shape. The same thing with the p orbitals. If you take the 3 p orbitals and look at them as a whole, it's what we call spherical symmetry. And so if we take a slice out of this, or a couple of slices, it loses that symmetry. And so a filled 3D is like a complete cake that's got its symmetry. And a half-filled, you think is half a cake, so it's unbalanced. But you don't slice the cake like this because of Hund's rule. We don't fill half the d orbitals first and leave the other half empty. We fill them 1 electron at a time, so it's half filled. And so if we have a half-filled orbital, then we've just removed half of it like this. Well, actually, I should have done the top half, but it doesn't matter. And so it still has that spherical symmetry, you see? And so a 3D5 is good, and a 3D10 is good. These are a little bit more stable, especially the 3D10, more stable. But the 3D6, even though these are inner shell electrons, it can be attacked. Well, how many? Do you think you can lose all 6? Pretty tough, huh? Maybe it loses 1. If it loses 1, then we go half filled. So maybe iron plus 3 is good too, right? Iron plus 2 is good, and iron plus 3 is good. Probably iron plus 4 is not good, because then we're going to have to ruin our symmetry here. So iron plus 4s, unless it's a very powerful oxidizer. If it's a very powerful oxidizer, then all electrons are fair game. All electrons. But there's different powers. So we can understand some of the chemistry based on the orbitals here. Actually, and so what we have is this. These elements are very interesting, especially zinc, cadmium, and silver. Silver is called a pseudo group 1, like these. This is group 1. Why is silver called a pseudo group 1? Copper is a bit more tricky. No, there's other reasons for copper. But let's take a look at silver. Tell me the electron configuration for silver. You could use a Nobel gas abbreviations of silver. So silver has how many electrons? 47. The nearest Nobel gas is krypton at 36. The nearest Nobel gas before.
Oh,
Yeah, so we're going to start at krypton, 36. So we'll start at krypton, which is 36 electrons. So the 37th electron goes where? 5s. Let's go ahead. We're going to fill that up. So it's going to be 5s2. And then 39th goes into the 4d. So we go 3d. 4d, 1, 2, 3, 4, 5, 6, 7, 8. 48. I'm sorry?
Why would it not be 49?
Oh, I screwed up. That's why I miscounted. It is 49. You're absolutely correct. 49. And so this is what it looks like here. This is 5s2 49. This is what's predicted. However, what's observed is this. Krypton 5s1 4d 10. This is observed. So what happened? What do you think happened?
Outer shell electrons got bumped down to the fourth.
Yeah.
Fourth
Right. So what happened is this. We pull up the 5s. This is the 5s. And then the 4d comes next. 4d. And this is 49. 49 is special because it's only one electron short of
4010.
yeah, 4010. And so what happens is this. Nature tries to find a balance in which it can minimize energy best as possible. So what it's going to do is it's going to take an electron and promote it here. And so it's going to cost a little bit of energy to promote it, but what you get back is a filled D subshell, which is more stable. And so this just happens automatically. You know, nobody does this. It is what's observed. And so what's observed is this. They only find one electron in 5s, but the 4d is completely filled. So we fill these one at a time. And that 4d subshell is like this. You know, it's filled. And so it's a little bit more stable than having a slice taken out of it. Having that slice taken out of it makes it less symmetrical, less stable. Now, this is the way it fills. This is the filling order, you know. But if you're an oxidizer, what are you going to see? You're going to see the outermost being the 5. The 5 squared is 25. This is 25 times further out versus 4, 16 times further out. So if you're an oxidizer, the first electron you're going to encounter is this. Even though these are more tasty maybe, but actually this is not because it's filled. This is going to be quite stable. And so what we do is for reactivity, this is the filling order, but for reactivity, we write the electron configuration for silver like this, where we separate the core or the inner electrons from the outer electrons. So we'll write it in numerical order, 40, 10, 5s1. And so these are going to be inner shell or core, and this is going to be valence. Now, for silver, do you think, well, for sure +1, you know, oxidizer comes in, takes an electron. But do you think +2 is viable for silver? No, not at all, because +2 would screw this up. Well, let's take a look at copper. copper, we get argon, 4s2, 3d9. So, we have this situation where we're one electron shy of this. And so this is what's predicted, but this is not what's observed. Can you tell me what's observed for copper? What's observed for copper is argon, 4s1, 3d10. And so as far as reactivity goes, this is the way we visualize the reactivity. It would be 3d10, 4s1. So if I were an oxidizer, I'm going to pluck that 4s1 electron off, right? But what about the 3d10? 3d10 shouldn't be touched because that's filled. It's a filled subshell, so it should be stable. And so copper plus 1 is no problem. Copper plus 1, we pluck that off. But what's the more common charge? Copper plus 1 or copper plus 2? Plus 2. And so it screws up that symmetry. Well, what did I just say about silver? You'll never see silver plus 2, but you'll always see copper plus 2. And so what happens with copper is there's a different reason that 3d9 is stabilized. 3d9, let's just do this as an aside over here. Copper 2 plus would be argon, 3d9. This 3d9 is stabilized by something else. Stabilized by something called ligand field. This is ligand field theory, but this is Chem 1B. We're not going to talk about it here. But what we can say is this. And gold is tricky too. Gold is plus 1 is very common for gold, but also plus 3. And there are other reasons it's stabilized. But silver for sure, the only charge is plus 1. Since silver works nicely, that's the example I want to use for this. Zinc works very nicely too. You know what the electron configuration for zinc is? Yeah. Zinc is, as predicted, it's be 4s2, 3d10. So zinc has how many valence electrons? 2. So zinc is always plus. To cadmium, cadmium is 5s2, 4d10. So cadmium is always plus 2. And so these are called the pseudo group 1. These are called the pseudo group 2 because they have the filled D. Subshell, this is unreactive. Now, there are some more exceptions here. Chromium, molybdenum, tungsten, these guys have electron configurations that aren't as predicted. Let's just take a look at chromium. What do we predict for the electron configuration of chromium? Well, I predict argon, 4s2, 3d4. This is what's predicted for chromium. Can you tell me what's observed for chromium? The way I visualize chromium is like this. Let's say I have a half a cake here. Half a cake that I sliced like this. There's one slice missing. Because this cake has 5 slices. So what do you think it is? Observed. What's observed is argon, 4s1, 3d5. That's it. That's what's observed because if we take one slice out of here and put it here, then it's good. But if we take one slice out of S, doesn't it screw that up? No, because S is a sphere. So if we take one slice, we just have a smaller sphere or something in that sense, you know? Although it's not really smaller. It's still spherical, so that's how it is. So S is not as impacted. Who cares if we have a half-filled S, in other words, or something like that. The P is kind of similar in that way. P doesn't really, it doesn't make that big of a difference here with P. It's the D's that we we see this difference occur. So writing electron configurations, we use the periodic table to do that.
Will that it only fills up to the 10 or to the whole if it's missing by 1 or if it's short by 1?
Right. If it's short by 2, like nickel, forget it. It's too costly in terms of energy. So let's just take a look at nickel. Nickel is argon, 4s2, 3d8. And so here we're 2 short. And so what we could do is we could promote 2 electrons here and fill up that 3d, but it's too much. It's too costly. How do I know? How I know is it because it doesn't happen. It's not observed. That's not. And so 1 electron appears to be okay to promote, but 2 electrons is too much. And so it stays as 3d8. Aluminum? Aluminum, aluminum is like this. Well, probably not. Let's go with, rather than aluminum, let's go with gallium. Do you see gallium? It's right below aluminum. And so let's do gallium. If we do gallium, what do we predict for the electron configuration? Okay, let's go back. Yeah, it would be AR, or argon, 4s2, 3d10, 4p1. And this is how we fill it. This is the filling order. But in terms of reactivity, it's going to look a little bit different. It's going to be argon. The filling order is how we fill it according to the chart. The reactivity order is just, you go numerical order. And so it'd be 3d10, then 4s2, and then 4p1. Okay, we divide these into inner shell, and outer shell. Outer shell would be the valence. And so if you're an oxidizer, you're going to attack, whether it's lower in energy or not, you're going to attack the ones that are closest to you. And so what we're going to see is we're going to have 3 electrons susceptible to attack here. And actually, this being filled D, these are going to be untouched. So gallium is going to lose 3 electrons, like aluminum. And in fact, your book summarizes it like this. These are called the main group, group A. Group A is the main group, the main block. And so this is the S and this is the P. That's the P. So group 1, group 2, group 3 is aluminum, group 4 is carbon, group 5 is nitrogen, group 6, the family, nitrogen family, oxygen family, fluorine family, helium family. These families have names. These are the alkali metals, alkaline earths. Aluminum doesn't have a special name. Carbon, it has a special name, but nobody uses it. Nitrogen, sometimes it's used. These are called the nicogens. Nitrogens and nicogens. Oxygen are the chalcogens. This one's used all the time. The fluorine family is called the halogens. These are noble gases. But they all have this. And so group 1 has 1 valence electron. And so pretty soon we're going to start thinking in terms of the valence electron. So sodium has 1 valence electron. So all the other electrons are core. And so if we're doing reactivity, we're going to show that. This is called the Lewis dot symbol. It's the symbol of the element plus 1 dot representing 1 valence electron. So lithium would be the same. It'd have 1 dot. Potassium, cesium, they're all the same. Magnesium has 2 valence electrons, so we show this 2 dots. Then it's 2. Aluminum, like gallium, has 3. Like boron has 3. And so it has the NS2NP1 valence. Silicon has 4, carbon has 4, so NS2NP2. Just change the number. So silicon would be 3, carbon would be 2 as N. Phosphorus, 5 valence electron. Sulfur, like oxygen, 6 valence, 6 dots. Chlorine, 7 dots. Argon has 8 dots, which is an octet. That 8 dots is stable. Typically, we divide the region around the atom into 4 spaces. When we draw these symbols here, and we like to pair up the electrons sometimes if possible. Sometimes not. We don't make any distinction between S and P because the S and P, it's not a huge difference in energy. Obviously, the P's are going to be attacked first. The P's will be attacked first, so there's 2 of them. Those get equal, and then the S. But here, which one are the S, which one are the P? We don't care. It's got 4. Does it make sense? Over here, we only have S, so we'll only have S. That's it. We got S. So those are Lewis dot symbols. We're going to be using Lewis dot symbols a lot. All right. So let's look at an application. Well, we did look at one application here, as far as chemical reactivity goes. We'll take a look at some more applications of using the periodic table. Predicting. One application is atomic size. Atomic size depends on 2 things. How many shells? The more shells, the bigger. So, for example, let's start off with lithium. Lithium is very small. We go down to cesium. Cesium is very big. Why? Because more shells. 1 shell. Cesium has how many shells? Yeah, 6 shells. If we take that 6th shell out, it's got 5 shells plus the 6th valence shell. Lithium only has 1 shell, valence shell, or 2 shells. Sorry, I think that's 2 shells, sorry. So obviously the more shells, the bigger, right? And also N, when we look at N, N equals 6. 6 squared is 36, it's big orbital. So a 6s orbital is like 36 times bigger than a 1s orbital. It's one way of visualizing it. Roughly, as far as the, so the more shells, the bigger. The fewer shells, the smaller. Okay, now there's one other thing that impacts the size, and that is Z. And so here, if we go up or down, it's the number of shells. We look at. If we go left or right, it's Z is the most important. What was Z again? Z is the nuclear charge. So let's just take a look at the second shell. Z is the number of protons. Number of protons is most important because if you only have 1 shell, we only got 1 shell. Let's say only 1 shell we're looking at. Then what's going to impact the size of that particular shell is going to be Z, the number of protons. And so let's start off with lithium. I'm going to blow up the size of lithium, make it a little bit bigger. So this is lithium. Now beryllium, beryllium has more stuff. It's got more protons, it's got more electrons. Even though it has more stuff, it turns out it's smaller. Why is it smaller? Beryllium is smaller. And then it keeps getting smaller. I shouldn't have started this small because when we get to neon, neon is going to be the smallest. And the reason is very simple. It's like hydrogen and helium. Which one's bigger, hydrogen or helium? Hydrogen. Hydrogen has 1 proton, 1 electron, versus helium. Helium has 2 protons and 2 electrons. Which one's bigger? You think helium's bigger because we've got 2 protons and 2 electrons, but helium turns out to be smaller. The reason is because those 2 electrons are in the same shell, in the same orbital. And so if we have 2 electrons here, and then I've got 1 electron here, then we got 2 protons. And we look at each electron separately. So you got 1 electron there, all of a sudden it's being attracted to 2 protons versus 1 electron being attracted to 1 proton. And so the net effect of this is that the electrons get pulled in closer to the nucleus because there's a stronger electrical attraction. And so each electron sees a +2 charge. The electrons try to stay away from each other. Why do electrons try to stay away from each other? Electrons try to stay away from each other because they're the same charge. So they don't want to interfere with each other. But sometimes they will. Sometimes they'll come in here and block or shield. But they don't always shield. You know, let's say this electron's jealous of the other electron, and so the other electron's trying to get all the attention from the nucleus, right? But the electron's not going to stay there and shield or block the other electron from the nucleus, correct? And so that just doesn't happen. It can, and so there is a little bit of shielding, you know, because they're free to move anywhere they want. However, there's not a huge amount of shielding. And so this is the reason why, as we go from left to right in the same shell, the atoms get smaller. Now, if we add another shell on top of this, obviously they're going to get bigger. And so let's take a look at the size trends here. So as we go across here, no, it's hard to see with hydrogen and helium. You know, this is 37, that's 31. But it looks like helium's bigger. Am I imagining it, or does it look like helium's bigger?
Probably totally does.
It totally does. That's so weird. That's really bizarre. Because helium is smaller. I mean, this is 37 what? 37 inches? What do you think this is? This is 37. No, hydrogen only weighs 1 atomic mass. Helium weighs 4. It's the size in what units? Would you say micrometers? It's picometers. Yeah, it's 37 picometers. So this is 37 picometers, this is 31, a little bit smaller. But take a look at this. Lithium is 152 picometers. Neon's about half the size, it's 71 picometers. So it's shrunk by about half. This is Z. Z is like a tractor beam. It pulls in the satellites, the electrons closer. So the higher the Z. Well, if we go here, lithium has how many protons? Well, lithium has 3 protons, sodium has 11 protons. And so isn't 3 protons versus 11 protons, isn't 11 protons a lot stronger tractor beam?
It's got more shells.
Yeah, it's just got more shells. So if we look at the 1s orbital in hydrogen, oh actually let's just go to lithium. If we look at the 1s orbital in lithium, the 1s orbital in lithium is tiny compared to hydrogen and helium. The 1s orbital is a lot smaller but since it's got more orbitals, it's going to be bigger overall. So lithium's bigger than hydrogen. And the same thing with sodium. Sodium's got 11 protons, but it's got more shells. So that's atomic size. You can see this is just repeated. Yeah. And so what's the smallest atom on the periodic table? What should be the smallest atom on the periodic table? Helium. What should be the biggest atom on the periodic table? The one on the bottom left, which is francium. Francium is radioactive, so we just usually say cesium. Francium doesn't live long, being radioactive. So that's the size, and then we're going to look at one more thing. We're going to look at something called ionization energy. Ionization energy, this is equal to the energy required to strip an electron. To remove an electron from a gaseous atom. So we have to vaporize the atom, get in the gaseous state, and then try to knock an electron off of it. This is called the ionization energy. Some things can lose more than one electron. If something can lose more than one electron, then we're going to have different ionization energies. So for example, the first ionization energy, IE, or I, is to knock off the first, and then the second, third, etc. There are two trends here that I could talk about briefly. Basically, it depends on the size. The ionization energy, what's easier to ionize, like cesium, a big atom, or lithium, a small atom? What do you think is easier to ionize? If you're an oxidizer, and you're trying to take electrons. So will it be easier to take electrons from cesium, which is a big atom, or lithium, which is a small atom? Lithium? Cesium? So we have a conflict here. Why lithium? Why cesium? Why do you think cesium?
I think cesium because the electrons are further away from the nucleus, and so they have less attraction towards it.
Yeah. Okay. Yeah. Well, yeah, that's right. If the electrons are further away, they're going to be weakly interacting with the nucleus compared to the ones that are closer, which are going to be more strongly interacting with the nucleus. So the ones that are further away can escape the nucleus a lot easier. It's like gravitational pull. You know, what's going to be easy to pull off the Earth? You know, the ones that are close to the center are the ones that are farther out in space. So the ionization energy goes with size. The smaller the size, the harder it is to ionize. So it's going to follow the same trend as size, you know. Hydrogen versus helium, which one's smaller? Helium's smaller. It's going to be harder to ionize. Why is it smaller? Because there's a bigger attraction with the nucleus. You know? It's got that tractor beam effect. So therefore, it should be harder to ionize helium. In fact, helium has the highest ionization energy on the periodic table. And what is that ionization? That's almost 2,500 kilojoules per mole to ionize helium. 2,500 kilojoules per mole is very, very difficult to ionize. What has the lowest ionization energy? What should have the lowest ionization energy on the periodic table? Which atom should be the easiest to pluck an electron off of? Cesium. Cesium for sure. or francium, so francium's radioactive. Unfortunately, cesium's not here, but take a look. Here's lithium. Sodium's a little bit bigger, so easier. Potassium's bigger, so it's easier. Cesium should be where around? A little less around here. And so if you look at potassium, it's around 400, somewhere in the 400s. So 400 kilojoules per mole is not much energy. And so that makes it easy to take an electron off, versus 2,500 kilojoules per mole, which is a lot of energy, which makes it hard to pluck electrons off. It still costs electrons, interestingly enough. If you want to take an electron from potassium, it's going to cost you energy. It's not free. Potassium doesn't give electrons for free, but it's cheap. Because it's cheap, it's easy to take, right? Whereas helium is very expensive. And so for something like potassium, water is very cheap, right? Not very reactive. It'll take it off. Water has enough energy to strip. But will water strip an electron off helium? Forget it. It's not going to happen. So this is it. And so it just goes based on size. So what's bigger, lithium or neon? Lithium's big, easy to strip. Neon is small, hard to strip. Sodium versus argon. Sodium's big, argon is small. But you see they're all kind of grouped around here between about 400 to 2,500 kilojoules mole. Like that. But there's some blips here. Do you see these little blips? These blips are exceptions. What's bigger, oxygen or nitrogen? Nitrogen is bigger. Oxygen is smaller, right? Because we're going across. So it goes nitrogen, bigger than oxygen, smaller, because it has more protons, right? And let's see, do I need to talk about the blips? I want to talk about the blips. I don't really want to talk about the blips. These blips are exception. We're going to discuss in detail in Chem 1A. But basically, this is it. The reason why oxygen should be harder, not easier. The reason why oxygen is easier, well, you don't have to memorize this for the test or anything. But nitrogen is like this. So if an oxidizer comes along, it's taking one of these three 2p electrons, right? Oxygen's smaller, but oxygen is like this. Now, if an oxidizer comes along, which 2p electron will be the easiest to strip? You know which one's going to be the easiest to strip? This one. Why? Because the electrons are both negatively charged. You're putting two electrons into one orbital, they're going to try to stay away from each other. That's called electron-electron repulsion. And so because of electron-electron repulsions, it makes this one easier to strip. And so that's what causes a little bit blip there. Boom, this one. Goes. What do we name these electrons? We give these electrons names. This one would be called the 2-1. Call it. Did I say 2-1 negative 1 or 2-1-1? I can't remember. It doesn't matter. If this was, we'll call this the 2-1-1 orbital. If this is 2-1-1, that's the 2-1-1 plus 1/2. This one would be the 2-1-1 minus 1/2. So we take this electron, the 2-1-1 minus 1/2. This is N, L, M, and the final one was S, N, L, M, S. We call those what? We call those numbers what? So the same thing happens here, phosphorus to sulfur. We're removing a paired electron versus an unpaired electron. We give a name for that repulsion. We call it the pairing energy. This is why Hund's rule is like this. We fill them singly, we don't pair because of pairing energy. Beryllium to boron, this is another exception. Boron is smaller yet easier to ionize. The reason it's easier to ionize is because we're moving a 2p versus a 2s. A 2p electron is easier to take than a 2s electron. That has to do with some other things. But ionization energy basically goes with the size. Now, we can ionize electrons. Let me just show you a chart of, actually, the book doesn't show this. It's going to show you a chart. And I wouldn't show you this unless the book mentions this. The first ionization, the second ionization, the third ionization. So I'd like to show you called successive ionization energies. Oh, I don't want to calculate. So the ionization energies vary from about 400 to, right, to, what did I say? 400 to about, what was the number? 400 to about 2,500. 400 to about 2,500. Keep that in mind. The 2,500 was the highest, right? But what we just looked at, it was what's called the first ionization energy. It's to remove the first electron off there. Now we're going to look at some other ionization. Helium is very unreactive because that first ionization energy is hard. Sodium is very reactive. You can look at the first ionization energy for sodium. We'll call it EI1. E for energy, I for ionization, 1 for the first. EI1, about 500. 500 is small. Those peanuts. Easy. Now, you're an oxidizer. You try to strip the second electron. Is it going to be so cheap? No, it's going to be like 5,000. So all of a sudden we jump from 500 to 5,000. It's like one of those things. You know, it's like one of those, it's like a sales tactics kind of thing. Okay, you're lured in because the first one was so cheap, and then they hit you with the second one. The second one, well, it's 10 times more expensive. You're going to pass on the second one. Don't you think? And so, this. Take a look at magnesium. First one, 738, not bad. Second one, 1451. Wow, it's getting more pricey. 1451. Third one, 7,000. No, forget it. Aluminum, first one, okay. Second one, third one was getting more expensive. This is more than helium. So why does aluminum go to +3? Why does aluminum go to +3 when it's going to cost you way more energy than helium going to +1? If helium goes to +1, it costs you less than 2,500. Aluminum going to +3 is going to cost you 600 plus 1,800 is 2,400. 2,400 plus 2,700 is going to be about 5,100. It's going to cost you 5,100. Let's say $5,100 to go from aluminum 0 to aluminum +3, whereas for helium it only cost you 2,400, half the price. So if you're an oxidizer, why don't you take off helium? Why attack aluminum? Doesn't make sense, does it? Well, it is because of the line, but you know, but helium is already at the line here. But in terms of energy, why? Let me tell you why. Because there are other factors. Do you remember when we were talking about metathesis? What are the driving forces for metathesis? Precipitation, effervescence, gas formation, stronger to weaker acid. All that has to do with bonds, forming bonds. And so the reason why aluminum can easily go to +3, even though it's going to cost you more than 5,000 kilojoules, is because of the types of bonds aluminum 3+ can form. It can form very strong bonds. And those very strong bonds help compensate for the cost. You know, energy is going to, it's going to calculate like this. The initial cost, think about an investment. The initial cost of this investment might be more. So you're going to go out, you're going to buy a bicycle pump. There's the $4.99 bicycle pump. versus a $30 bicycle pump. And you go, wow, $4.99, I'm going to get that pump. It's only $5, right? And you get that bike pump, but how long does it last? Not very long. Versus the $30 is going to last forever, right? Well, the same thing. The initial investment is kind of costly, but the return on investment here from the bonds that it forms is well worth it. And so the bonds you can make from an aluminum 3+ are very strong. It forms like good precipitates, like aluminum oxide. If you're a geologist, you know about aluminum oxide. Aluminum metal used to be a rare metal, rare and precious metal. Did you know that? Why? Because aluminum metal was gotten from refining aluminum oxide. Refining aluminum oxide used to be incredibly difficult and incredibly expensive because aluminum oxide is an incredibly stable ceramic. They use aluminum, one use of aluminum oxide, they use aluminum oxide in like nuclear bomber pilot goggles. This is one of the applications I was reading about, because the aluminum oxide, a single crystal of it is totally transparent. And then they dope it with certain chemicals so that with an electric switch, they can make it block out all light. And it's incredibly tough. It's super strong stuff. It doesn't melt or whatever else. But anyway, I used to use aluminum oxide cooking pots. These aluminum oxide cooking pots, I'd heat to 1200 degrees C, 1300, 1400 degrees C, no problem. In fact, I looked through a cookbook with a little aluminum oxide cooking pot like this is a couple $100, And so I had all kinds of aluminum cooking pots, aluminum oxide cooking pots. It's an incredible ceramic, alumina. It's very hard. It's like a 9 on the Mohs hardness scale, so just below diamond. And it's impossible to melt, impossible to dissolve with acids, with bases. It's very unreactive. But anyway, it forms strong bonds, so those strong bonds will pay off in the end. So anyway, do you know the difference here? The blue are what we call outer shell electrons. Oh, the time. Shoot, I forgot about the time. Do you guys, in fact, I was going to ask you about this. Do you guys want no break and then just end earlier, or do you guys want a break in the middle of class?
That's how long earlier.
Well, our break is normally like 10 minutes, right? Do you want to forego the 10-minute break and just end 10 minutes earlier? And I'll just go talk straight through. That's fine? All right. Then I'm just going to keep going then. We're going to skip the break.
So what time we at?
Well, normally, what time do we end on Wednesdays? At 25 or 35? At 35? So we'll end at 25. You want to do it that way? Or do you want to take a break now?
No, let's do it.
All right, we'll just end 10 minutes earlier. Skip the break. Well, anyway, the blue are valence electrons, the red are the core electrons. Even though the core electrons can react, it's going to cost you a heck of a lot of energy to get those to react. And so it is possible to form a sodium +2, but you'd need an ultra powerful oxidizer to do it. Something more powerful than fluorine. Can you think of an oxidizer more powerful than fluorine? There are, but they're very exotic. I can think of one, although I don't know if it forms sodium 2+. One of the most powerful oxidizers I can think of are alpha particles. Have you ever heard of an alpha particle? Alpha particles are released by the radioactive decay of certain elements, and it's called alpha radiation. Alpha radiation is very dangerous. It's one of the most dangerous forms of radiation there are, but it's so easy to protect yourself from alpha radiation. You know how you can protect yourself from alpha radiation? A piece of paper. Because alpha particles, the reason they're dangerous is because they're extremely powerful oxidizers. Why are they extremely powerful oxidizers? Because you know what an alpha particle is made of? Alpha particle is made up of 2 protons and 2 neutrons. It's the nucleus of a helium atom. There are no electrons here, and so you got the nucleus of a helium atom. It wants electrons. It's extremely small, and so it's extremely reactive. Therefore, it's really easy to protect yourself because a piece of paper will shield you from alpha particles because paper is easy to oxidize. It will oxidize the paper. When it oxidizes the paper, then it forms helium. Well, is helium very dangerous? No, it's not dangerous. Or, you know, a piece of glass will shield you from alpha particles. No, it's easy. Whereas gamma radiation, can you protect yourself with a sheet of paper? No, forget it. Gamma radiation is high energy light. Alpha particles is what we call particle radiation, not light radiation. X-rays, you aren't going to shield yourself. You need something else. But going back to this, yeah, you can see, you know, sulfur plus 6 is not happy, but sulfur plus 7 would be incredibly unhappy. And so sulfur can be in the plus 6 oxidation state or in the minus 2. You know. So what we're going to look at here are the chemical families. Chemical families here. Alkali metals. Lithium has a ionization energy less than 500, so even water can oxidize lithium. So here water is oxidizing lithium, forming lithium hydroxide and hydrogen gas. This is a single replacement type reaction or redox reaction. We use the chart method. It's hydrogen gas and steam coming off of that. Which one's easier to oxidize, lithium or sodium? Sodium. Sodium's easier to oxidize. So here's water on sodium. It gets so hot, the hydrogen gas ignites, causes a little explosion. Here, it's not hot enough to ignite the hydrogen. Which brings us to another question. If sodium is easier to ionize, then which will be a better reducing agent? Sodium or lithium? Looks like sodium is a better reducing. It's more reactive than lithium. But I've been trying to drill this down. What is the best reducing agent on the chart?
Sodium. No.
Lithium. This shows that sodium is better. So what's going on? In fact, what's better, sodium or potassium? Potassium. Potassium's even better. In fact, potassium reacts much more violently with water, although you can't see it from here. It's way more violent. Because potassium is a lot easier to strip electrons. It's a big atom. A big atom's easy to strip electrons. Lithium is a small atom. Harder to strip electrons off. And so why am I drilling this down? Shouldn't the best reducing agent be cesium? Cesium should be at the top of the chart. Or at least potassium should be at the top of the chart. So potassium or cesium should be at the top of the chart, not lithium. So let me flip back to the activity series. That was in chapter 9. All right, some stuff makes sense. This makes sense. Sodium versus potassium. What's better? Potassium. Why is lithium there? Potassium is much more violent. Sodium is a heck of a lot more violent than lithium. Why is lithium at the top? All right, the reason why lithium is at the top is it's kind of like the tortoise and the hare type situation. Sodium and potassium react much more violently, much faster than lithium. Lithium reacts much slower, much less violently. But lithium keeps going. And what happens is lithium forms more stable bonds in the product than sodium and potassium. Because lithium, the reason why it forms more stable bonds in the product is because of this. Lithium forms the lithium ion, the sodium ion's like this, and the potassium ion's like this. So which one is going to have stronger electrical interactions? The lithium, the sodium, or the potassium? Well, do you guys remember from charge density, which one of these is the most reactive ion in metathesis? This is why alpha particles are so powerful. Alpha particles are so powerful because of